A brief introduction into what fiber optics exactly are is that they're these thin, flexible strands of glass that are encapsulated in what is called right here a cladding and a plastic jacket. The cladding being a less refractive glass than the one that's in the core. And they're able to transmit these signals over a long distance and with a minimal loss due to this cladding. Because this cladding is able to refract the light from the core, any excess, and back into the core, making it travel farther along. And as far as a brief history for fiber optics, they are first experimented on by John Tyndall in the 19th century, and it's actually really interesting the way he came about experimenting it and observing it was he used light within a stream of water, and so his stream of water was almost the fiber optic itself, and he was able to observe how light traveled through that. Now, in the 1950s, that's when they first started actually using applications for fiber optics, primarily with the development of the fiberscope. It was a device that used glass fibers to transmit images. It was very revolutionizing at the time. Uh, then in the 1970s, there was the invention of low loss optical fibers for telecommunications. These were just really high purity glass rods, glass fibers that were able to transmit these light signals with clarity. Because the more clarity you have, the more pure, the longer it can go without obstruction or losing any due to those impurities. And so, in this presentation, my goal is to explore the key properties of fiber optics, understand fabrication and how the quality is tested, as well as examine the industrial applications of fiber optics. Now, as far as key properties for fiber optics, it has two main ones, physical and chemical. And as far as physical properties, it's made of a silica-based glass most of the time, but it can also sometimes be used with polymer fibers. It's very thin. It's bigger in diameter than 125 microns usually, making it highly flexible. Now, the optical transparency and refractive index. Optical transparency refers to the ability for the fiber to transmit light with minimal loss, whereas the refractive index refers to the how much it's a measure of how much light bends when entering the fiber. And so both of these are used to measure exactly how efficient a light fiber is at transmitting light. Now, as far as chemical properties, it's very corrosive resistance. You know, it's the glass core. Glass is highly corrosive resistant, as we know, use it for beakers and such in chemistry, and it can last decades due to this corrosion resistance in harsh environments. The chemical structure is mainly of silicon dioxide, which is essentially fused silica glass, but a lot of times to make the fiber optic, it is paired with a dopant to add and modify its refractive index, in which the most common dopant would be germanium dioxide. And the way it works is that it enters the lattice of the silicon dioxide, and it only replaces every few silicon dioxide, not every single one, but just enough to strengthen those fibers and make it less refractive and more clear without breaking the structural integrity. Now, as far as the tensile strength and durability, it has a high resistance to pulling forces with an elastic modulus of 960 to 280 kilopascals. It has high impact resistance, and it was able to withstand bending without breaking. Now, additional considerations when using this is temperature resistance. It's able to operate in extreme temperatures, -40 to 85 degrees Celsius. Its efficiency at signal transmission is very high. It's able to communicate very fast and very long distance without minimal loss of information. And it's suitable for underwater as well as high temperature. So it's an all around environmentally sound and sound way of communicating. Now here I actually have a diagram in which the fiber optics are manufactured, and it all starts with the preform. It's this big giant solid piece of glass that's selected for its higher purity silica, and then dopants which have been added depending on its use to either increase or decrease that refraction. And that preform is heated up in this one space and pulled through this one small nozzle. And once it's pulled through, it gets stretched out really thin in a controlled manner, and it's once it's stretched to the desired thickness, it gets cooled down. So it no longer come to form or malleable. And after becoming cool, it gets coated with polymer coatings to protect against mechanical damage and just the fragile glass inside in general, and it's able to also receive its UV curing and buffer layers, which is able to enhance its durability and integrity, which is this next step afterwards. Now, there's been refined techniques which have been advanced. There's chemical vapor disposition, which will actually increase the. Now, going back onto that preform I said I would show y'all before, this is what a preform looks like before it's extruded. And just to scale, here's a person next to said preform. It's really long, really big. It's a solid piece of glass, essentially, that gets slowly pulled out thinner and thinner throughout the whole piece. Now, after the fiber optics has gone through its manufacturing phase and it's gotten received its UV coating, it's gotten spooled up, all that good stuff, it gets through a quality test and procedure standard. And it goes specifically through an optical transmission testing, in which it's a process that measures the degradation of a light signal as it travels through an optic cable. And the way it does this is it checks how much signal is lost, attenuation, and how much it spreads out, dispersion, as it travels through the fiber. Now, it also undergoes mechanical stress and bend radius testing to be able to apply real-world applications and understand what kind of complications may come and with how we lay it out. And right here, as you can see, I have a diagram that shows the bending testing, which the minimum bend radius that most optical fibers can go, as well as here is the fiber optic transmission testing. It sends it out and then receives another signal as it comes back, and then measures it as they go through and pass through that fiber optic. It also has to go endure environmental resistance testing, as these are going to be cables and such that are in the power lines or underground and wouldn't be able to need to be able to withstand such environmental factors if they're going to be in place and secure in our internet, as the internet and communication is one of the most important things in society today, in my opinion. Now, as far as industrial applications for fiber optics, the main one would be telecommunications. It's used for data, for phone, as high-speed internet. It's also used for your Wi-Fi just in your house. It's been mainly used today and has been implemented nationally in a very huge way, as it was the leading high-speed internet for a while. But as we move into satellites and their capabilities, we'll see how that continues to be. As far as the medical industry, it uses it for its endoscopic imaging and laser surgery. Lasers require a lot of information to be able to go through at once, especially light, as a laser is just light with a high concentration and a high amount of light concentrated within that one beam. And as on the same page of like the lasering, industrial automation uses it for their laser cutting and welding in the same way, but within a different application. It also uses them for the optical sensors and real-time monitoring, so it's instantaneous. The process, you're able to see it and be able to adjust your manufacturing process. And it can also be used in defense and aerospace, as it provides secure communication networks and optical guidance for missiles and surveillance systems and such. And here I have a diagram in which you can see industrial applications, the internet, the two major things, but it also can include robotics. And the way it does this, it provides instantaneous feedback to each part of the robot, in which I think is the biggest thing when it comes to robotics, is the delay, in which you want ease of access, and to make things look fluid, they need to have almost no delay between each action. And that will just about do it for my presentation on fiber optics. And just as a quick recap, I talked about how fiber optics are vital for today's communication and internet capabilities, as well as how they have a unique physical and chemical property that allow them to be durable while still transporting information at extremely high speeds with this clarity and fragility to them. And the stringent processing and how they're made and the way that they're tested for quality to be put into use within today's modern industrial scene. Now, as far as the future trends and innovations, there's been developments in hollow core and photonic crystal fibers, which just increase the speeds and make it so that it can hold all that information within the light source way better and travel way faster as well. And there's also been advancements in the quantum communication and high capacity networks as well, along with these fiber optics as the base. And I believe growing demand across the industries for these fiber optics is going to increase the importance for the technology and innovation that involves these very unique and very cool sort of glass fibers that are just seamlessly able to transmit information sort of just instantaneously almost. And I think it's really cool how we're able to just get information from light and then send that light down a line, and it happened just like that. Thank you for reading my presentation, and I hope y'all have a blessed day.